talk about something exciting about single-source sorted path. So consider an vertex and MS diversity graph where you have essentially non-negative real weight and the source S. So the well-known single-source sorted path problem basically asks you to find all the sorted paths from that vertex to every other vertex. So in particular, we are thinking about the comparison addition-based model. So I just said the edge weights are real, so you can only do addition or comparison between the edge weights. So for example, you cannot do like hashing or stuff when sometimes that's available when the weights are integer. So that's only you can do. You can only compare or add two weights. So for this kind of problem, there's this well-known Dijkstra algorithm, which was known like a very long time ago. And it's probably one of the most iconic algorithms to be taught in the introductory course. So this algorithm, I believe everybody here is very familiar with it. So essentially, you just keep looking for the vertex with the minimum distance, and then you extend it to the neighbors, and then update the distances, and then you keep doing it on and on until all the distances have been computed. So as you can see, this is implemented with a priority queue, and then if you use this priority queue, if you use velocity to implement it, you can get a running time of big O n plus n log n. So essentially, this is what we have all known about this algorithm, and so it's a very famous algorithm, and it has been known for a long time. So it's no wonder that people have been trying to improve it, and there have been some partial results. Firstly, for integer weights, there was an algorithm already that has instead of a log n dependence, has a log dependence. But it only works when the graph has an integer weight and the weights are sort of bounded by the upper bound C. So it doesn't work in general, kind of a real weight situation. And also, if you limit our perspective to only undivided graphs, then in 2005 there was also an algorithm that worked when there's not a big edge and a small edge, so the ratio between any two edges is not too big. The algorithm will work. And very recently, there was also an algorithm that beats Dijkstra by like a polymorphic factor. And unfortunately, the algorithm only worked for undivided graphs and was also randomized. And in this work, excitingly, we have an algorithm that beats Dijkstra also by a polymorphic factor. And more importantly, it's not only deterministic, but also works for directed graphs. So essentially, it's saying that Dijkstra is truly not optimal. But before I go into the algorithm, some of you might be saying, hey, I think you are bullshitting because I heard about the very famous result from 2024, in fact, the best paper from 2024. It's essentially saying that Dijkstra is universally optimal in this kind of a comparison addition-based model. But it's important to know that that result requires us to output the distances in increasing order. So what does that mean? What they showed is, let's say, for example, the graph is a blossom. In this case, if you want to output the distances in increasing order, you essentially have to sort all the weights here. So essentially, you're asking for a comparison-based method to sort all the edges increasingly. So as we all know, that is basically an organ. And that's what, of course, this kind of a implementation is also an organ. So indeed, in this case, you can see that Dijkstra is optimal in this sense. And on the other hand, if the graph is a chain, so in this case, instead of sorting the distances, you can just follow the chain, and so all the distances have already been sorted by us. So we no longer need sorting, and then we can just compute all the distances in linear time. But importantly, they propose that a variant of Dijkstra can also run in linear time in this kind of a case. Think about if you run Dijkstra here, the heap will always have only one element, which is the next vertex, and in this case, there's no log n running time. So you can see that essentially they show that no matter what the graph looks like, Dijkstra is universally optimal, but it only works if you want to output the distances in increasing order. So obviously, you don't have to output the distances in increasing order if you only want to compute them. And since the algorithm does not actually output the distances in increasing order, their result will not apply. So it's kind of like a orthogonal and also weight result compared to our result. Okay. So with that settled, I will begin describing my algorithm. So first I will describe a kind of a variant on single source sorted path called the bounded multi-source sorted path problem. So first I will give the definition. Consider instead of having a single source starting with distance 0, instead we have multiple sources starting with kind of an initial distance. So in this graph, basically all the numbers here are distances. So this is distance 3. And so here we have 3 initial vertices with initial distance 0, 1, 5. So we want to compute the distances from those vertices considering those initial distance. For example, this one has a distance 3 because it's from this vertex, and this already has a distance 1, so it's 1 plus 2 equals 3. Basically, we're asking us for like a multi-source version and initial distance version of the sorted path problem. And we also have an upper bound b. So instead of computing all the distances, we only need to compute the distance that are less than b. So for those vertices, the distances are more than or equal to b. The algorithm does not have to compute them and can leave them unknown. So this is kind of like a extended and kind of extended variant version of the single source sorted path. So
why isn't the 5 in the previous study? Why doesn't the 5 get the next vertex? Like the vertex to the right of 5 has this 2 to the master.
yeah.
So why was that not included in the
Because this one?
yeah. Why wasn't the vertex to the right directly to the right of 5? Why was that not included?
This one?
Yeah.
Because it's more than 6. It's 5 plus this one will have a distance of 7.
Oh, and the 5 is the distance.
Initial distance.
Yeah, those are the distances.
Oh,
Those are not vertex indices. Okay. So why are we considering this kind of a little bit awkward version of single source sorted path? The reason is it turns out that there's a self-contained divide and conquer method for this problem. Meaning that all the recursive subproblems will still be an instance of bounded multi-source sorted path problem. So I'll give a very simplified version of how it works. Suppose we're given a B prime, which is essentially an oracle that can divide the vertices into 2 equal halves. So let's say B prime equals 4. This will divide the problem into 2 equal halves. 5 vertices with distance less than B prime and 5 vertices with distance more than or equal to B prime. And so in this way, we can divide the problem into 2 halves, and we want to compute these distances for the first problem and this distances for the second problem. So if you want to solve the first half, it's equivalent to another instance of bounded multi-source sorted path problem, where the initial set contains all the sources that have a distance less than B prime, so the red vertices, and the new bound is B prime. So we just call it on the red vertices with the new bound B prime, and voila, the 5 vertices here will be computed with like a recursive call. And for the second half, obviously we also need to contain the source set within the source set the purple vertex, which is the vertex that has a distance greater than or equal to B prime. But this is not sufficient because there can also be a path that starts from the left half and continues all the way into the second half. And you can see that if we only include the purple vertex, we will miss this path because it doesn't even visit the purple vertex. So meaning that if we want to compute the second half, we also have to contain the source set for the second half also have to contain the set of all neighbors for the vertices computed in the first half. So in this case, you have to contain the blue vertex. So you have to call the second subproblem starting from both the purple vertex and the blue vertex. And then this way we can solve the second subproblem as well. And then we just combine them, and then we just compute the distances for all the vertices. So this is how essentially we can divide the problem into 2 halves. And in our actual algorithm, instead of dividing the 2 halves, we will divide into multiple paths, like a quasi-polynomial number of paths. And then we saw that by kind of taking care of the continuation from the previous path to later path, we can still do it, even if it's more than 2 paths. Okay, any questions so far? Okay, so now we will show that now that we have given like a very high level of what the algorithm is like, and what kind of a variant we are solving. We'll first show that unfortunately if we just do this, we did not really beat extra, and then we will need some extra technique for previous pruning to go beyond one kind of extra. So firstly, let's say we just implement the dividing counter as this. What is the running time? In the worst case, the source set S can contain all the vertices. So let's say we do a T-way dividing counter. So as I said, dividing counter doesn't have to be two-way, it can be multiple ways. So in this recursion problem, we have to decide essentially for each vertex in the source set which subproblem it has to fall into, so that we can just divide it into subproblems. So essentially we have to do the binary search into the T path to decide which of the subproblems it will go into. So it's like not T times for every vertex in S. And then unfortunately every vertex incurs not T times every level, and then because it's a T-way dividing counter, it's not n over not T level. So very sadly, we still spend not n times the level, and then if all the vertices, so the running time n not n. So this is not better than the extra. Which is unfortunate, but we will show that there's an idea that we can use to further go beyond the extra. So the idea here is instead of binary searching for every vertex in S, we can use that procedure that reduces size of S by like a considerable fraction. And then instead of binary searching all the vertices, we only have to binary search on a small fraction of the vertices, essentially saving off the running time. Okay, so as I said before, the reason why it doesn't go beyond extra is because the source set can contain all the vertices, and in that case, you have to essentially do the binary search for every single vertex, and this is very costly. So the idea here is before we do this kind of a division using binary search, we use the procedure called previous pruning to shrink the size of S by polynomial factor, and so that binary search only needs to be done on like this small fraction of vertices instead of all the vertices. So how is this done? We show that for any parameter k, there is an algorithm that ideally runs in the size of k, size of S times k squared time, and then you can find the size of pivot E, and then we can also compute a bunch of distances, so that for every sorted path, for every vertex that uses a non-pivot vertex, the algorithm will also compute the distance. So you can see that what the algorithm does here is, for those source vertices, you compute two pivots in purple, and you also compute a bunch of distances, but some of them are not computed. They only compute some of them, but not all of them. But importantly, for any vertex, for example, the red vertex here, that sorted path is actually from a vertex that is not a pivot. So this one is not a pivot, it's not in purple. It guarantees that the vertex will have its distance computed. In other words, let's say a vertex does not have its distance computed, then the sorted path must be from a pivot, right? So this vertex is not computed, and you can verify that it's indeed from this pivot. So what it tells us is the only remaining work after this algorithm is to compute the remaining distances from pivots. So the non-pivots are basically already taken care of. It means that instead of still computing the sorting distance from all the source vertices, we can just compute the sorting distance from pivots. And because the size of the pivot is now k, it is essentially saving off k on the size of S. And then, but the running time is like size of S times k squared ideally. So essentially we have overhead of k squared. So this means that we can balance the running time by setting k to be not to the 1/3 n. And then we just cut not to the 1/3 running time from backward. So that's basically the high level idea. So now I'll talk about how this is done. So this is actually pretty simple. You just run the Bellman force step k times to compute the sorted path from the source left S. The way this at most k vertices, and at the same time creating a sorted path forward. So here we have all vertices color coded, and then we can search 3 times, so 1, 2, 3 for every single vertices. So vertices, and then we create the red tree, the blue tree, the green tree, and the purple tree. So those are sorted path trees. So we essentially just let the pivot be the vertices in S, such that if the tree that the tree that is the root of has a size that is at least k. So here we are looking at trees that have a size at least 3. So you can see that the red tree has way more than 3 vertices. The blue tree does not have more than 3 vertices, and the green tree also has way more than 3 vertices, and the purple tree does not have 3 vertices. So now the pivot will only be the red node and the green node. So you can see that firstly, already the at most n/k vertices can have at most n/k tree can have a size at least k. So the size of the pivot is indeed at most n/k. So that means that indeed the algorithm does not output too many pivots. But is this algorithm correct in that all the vertices that does not use the pivot indeed has its distance computed already in the gamma both vertices? You can see that all the remaining vertices that have a distance not computed must be from the bottom layer, that's in the brown rectangle, must be using those edges going beyond the tree. So you have to go down here to find the vertices that have a distance not computed. But you can see that if a sorted path tree has a size less than or equal to k, then you can never reach the bottom layer because it's like a Bellman for k step. You have to go 3 times. You have to go k times to reach the bottom layer. So like this tree does not have a size over 3, so it doesn't even have a chance to reach the bottom layer. So you can see that if a tree has a size less than or equal to k, it does not reach the bottom layer. In other words, it does not have any access to the uncomputed vertices. So in other words, all the distances from that tree must already be computed. So indeed, the remaining work must be from a pivot vertex. Okay, any questions so far? So now that we've gone through the high level idea of the algorithm, I'll go to like a technical hurdle. So far we assume that we can find an appropriate bound that can be used to divide the problem into appropriately sized subproblems. We also assume that we can indeed do the division, like for every vertex we can just decide which subproblem it goes into. So this kind of oracle stuff. Obviously we don't have the oracle. So in reality, instead of knowing all the distances, like in this case, and evenly dividing them into subproblems, and then evenly sort of allocating all the vertices into subproblems. In reality, there's going to be some distances that are unknown, and then some distances that are known. So you can see that in reality, some of them are unknown in gray, and some of them are known in green. So the split points have to be guessed based on the known distances. So in this case, we are just going to place the split points so that if you only look at the green regions, the known vertices, it looks like we have partitioned the problem into equal size. So you can see that this problem is very big, but then if you only look at the green part, it looks like it's as big as the other subproblem. So even if you have, so just to kind of maintain the split point, we have to use the data structure because as the algorithm goes on, new distances might be known, and then the split point needs to be sort of updated. So for example, maybe halfway into the algorithm, we know some new distances in this area, and then this problem we don't realize it's actually too big. So what the algorithm would do is it would just split that problem into 2 new subproblems that look identical in size if you only look at the green region. So basically, the algorithm will have to do that occasionally to kind of balance all the subproblems using like computed distances. And even if that's the case, sometimes without going to the subproblem, we can never truly know if the subproblem has been correctly sized. So what that means is that we might still accidentally commit into a subproblem with the wrong guesses, only to find that there are too many vertices inside this kind of interval. So let's say we think BI-1 to BI is the appropriate division. Like we think there shouldn't be too many vertices here because like we only know this distance in green. So based on known distances, it seems like we can just go into the subproblem without having too much trouble. So what's going on is, okay, we commit into the subproblem, so we are in this subproblem now. And we come more distances and realize, actually, there are so many more vertices in this subproblem than we expected. So we kind of underestimate the workload. So what's going on is, the subproblem, so what we'll do here is we will just prematurely end the subproblem and go back to the parent. So here the subproblem is supposed to be Java, and we prematurely ended after only computing up to this point. And what we will do is we will just rebalance all the remaining work. So we have those distances that are unknown in the subproblem, and then we will just rebalance all the remaining work. So it seems like we are good to go again, and then we just commit again, and then whenever there's a problem, we go back and do the same thing on and on until we computed all the distances. It is kind of like a little and a kind of a high level of we are able to deal with that. Any questions so far? Okay. So now that I have gone through the algorithm in detail, now we will look back at it in like a very high level and kind of explain why we were able to go beyond Dijkstra, like what is the main reason that the algorithm works. So in Dijkstra, we kind of have a frontier, so that is the heap, and we need to keep finding the closest vertex in the frontier. So essentially sorting the entire frontier. So let's say in the case where if a single vertex connects to every other vertex, in this case the heap will contain every other vertices, and then we are sort of just finding the closest vertex in the one by one. So because it contains all the vertices, in the end we sort all the vertices in increasing order. So it's essentially like sorting. So this inherently has a sorting lower bound if we just do this and let the frontier contain all the vertices. And so what we are able to do to go beyond the sorting barrier is by looking ahead case step. So we recall that in this kind of a pivot pruning procedure, we use the Bayerman forward case step. So we look forward case step, and then we use that to cut the size of the frontier to only one overtake of its original size. Obviously, it has kind of an overhead, so we can balance out and get like a moderate time saving. So this eventually enables us to go beyond the sorting barrier. So this is eventually like by looking ahead and cutting the size of the frontier, and we were able to do this. And finally, I want to mention that if you just do this, it's not sufficient because the frontier is very dynamic and intractable. So because new vertices are coming in and then vertices are going out. And so we essentially re-express the algorithm using a divide and conquer procedure. So that the frontier is now simply the source step S, and it is static. And since it's static, it enables us to use a static Bayerman forward-based procedure that can do a pivot pruning and then cut the size of the frontier to like only a small fraction. So it is worth mentioning that divide and conquer has traditionally been useful in transforming a dynamic process into one that is more static. So think about sorting integers. One way we can sort is by using a binary search tree, which I believe nobody actually does that. But then let's say we are stupid enough to solve the integers using a binary search tree. You can see that the binary search tree is dynamic. So new integers are going in, and then it has some rotation setup because depending on your implementation. So it's very dynamic, and then there's no way we can sort of do anything about it. But then there's also a way you can sort the integers, which is merge sort. So if you do merge sort instead of a dynamic binary search tree, now every time you only have two static frequencies, static increasing frequencies that you have to merge into one static increasing frequency. So you can see that compared to BST, merge sort is way more static locally. And then indeed, binary search tree is kind of like Dijkstra, where the heap is dynamic. And then merge sort is kind of like our divide and conquer procedure, where we have a static source step, and then eventually that's kind of what enables us to do this kind of a pivot pruning procedure. Okay, any questions so far? Okay. So now that I've gone through the main chunk of my talk, I'll be doing some comparison with the previous algorithm, and kind of a single source for defined problem. So in 2023, there was, as I mentioned, there was this kind of undivided graph algorithm that is extra in a randomized way. So the way that algorithm works was essentially by sampling a small set of vertices and then bundling every other vertex to the closest vertex in the sample. And then with some tricks, the frontier using our terminology only need to contain the samples, and this is how they can say a factor from polymorphic technique. And in our algorithm, instead of doing random sampling, we use a pruning procedure. So it's like instead of a simple randomized procedure, it's a more sophisticated deterministic procedure. And then that's what enables us to make the algorithm not only deterministic, but also work for divergent graphs. Finally, there was also a work in 2024 that also be satisfied in the related problem of single source bottleneck path problem. So in the single source bottleneck path problem, instead of finding, so the length of a path is not the sum of the weight, but the maximum weight. So instead of minimizing the path with regard to the sum of the weight, we minimize the maximum weight on the path. So in this problem, they show that we can beat Dijkstra because Dijkstra naively could also solve that problem. So the algorithm is again very different from ours, except for the fact that they also use a dividing concept procedure that recursively divide the problem into quasi-polynomial number of parts. So we can see that it's kind of a division into quasi-polynomial number of parts found success in multiple kind of multiple problems in this graph theory context. And then also not mentioned in our paper, you could just replace additions with max operation in our algorithm. You can adapt it to also work for single source bottleneck path problems or many other variants of the single source path problems. So in fact, it makes our algorithm the first deterministic improvement over Dijkstra in this single source bottleneck problem as well. And that's the end of my talk. Thank you for listening.
Keep trying to think of lower bound too. Is that
Oh, yes, sure. So the lower bound, I think currently there's a barrier which is m squared is not there. And the reason why I think there's this barrier is so here we are essentially looking ahead k that with like a k square overhead. And we think that k square overhead to be at least k, because if you look ahead k steps, essentially you are introducing k more workload. So you're like using the k more workload to save off 1 over k elsewhere. So like this kind of a balancing stuff that we cannot get rid of. And if you replace the k square with k, it's exactly the not there.
question? It's like Xiao Lian.